Okay, we need to talk about reaction stoichiometry. This is the idea of taking balanced reactions and the moles to gram, grams to mole conversions and kind of combining everything. I can't say it's the most fun stuff in the world, but I definitely will tell you if you ever make it to organic chemistry, it's about the only math that ever shows up. This stuff definitely never goes away. So let's just look at an example. Okay, let's say we have carbon monoxide with 2 moles of hydrogen forming CH3OH. Okay, not a real likely reaction, but technically possible. Okay, in terms of interpreting this reaction, most people when they look at it would say, oh, we have 1 molecule of carbon monoxide reacting with 2 molecules of hydrogen to form 1 molecule of CH3OH, which is methanol. Okay, and that is not incorrect, but it's probably not the best interpretation. The best interpretation is that for every 1 mole of CO plus 2 moles of H2, what happens is you form 1 mole of CH3OH. So, thinking about it in terms of moles is probably the most likely useful version of this. We can't think of it in terms of grams. We can't take 1 gram of this and make plus 2 grams of this to make 1 gram of this. That doesn't even like add up. Okay, you're just magically losing 2 grams of stuff. But it does work in terms of moles. Okay, so let's try an example. So let's say we ran this reaction. Okay, let's say we had this balanced equation already set up, and we want to know how many moles of CH3OH could be formed from 0.413 moles of H2 and an excess of CO. So let's say we have a whole bunch of this and we have 0.413 moles of this stuff, and we want to know how many moles of this can we make. So essentially what we use is something called the mole ratio. It's a 1 to 2 to 1 ratio. Okay, so as long as this is a balanced equation, that ratio is going to work out. So we have 0.413 moles of hydrogen, and based off this balanced equation, we know that for every 2 moles of hydrogen, we should be able to make 1 mole of this. And that's our mole ratio. So literally, you're just taking this number and dividing it by 2. Good. All right, so you're going to take basically 0.413 divided by 2. And the math works out to be 0.2065366, 0.207, I think is the answer. Not real complicated, right? This does mean, though, that you will need to have the balanced equation in order to do any of this stuff. That's also why these are called the stoichiometric coefficients in the front. It's based off the idea of stoichiometry, the balanced equation. Okay? The problem is, in the real world, we almost never do it this way. In the real world, we do everything based off grams. We measure out grams of stuff. We never have moles of things. So let's try another example where we have grams instead of moles. But the idea of, I guess I could label this, the idea of a mole ratio based off the balanced equation is the main new concept here. Okay, so let's try an example. All right, let's say we have this equation. CO plus 3H2 forms CH4 and H2O. Okay, already balanced. And let's say we started out with, I don't know, 20.0 grams of this, and we want to know how many grams of this can we make. Okay, well, the problem is these are only related by moles, they are not related by grams. So let's try this. These always are the same 3 steps in the same order. So what we're doing is we're starting with 20 grams of carbon monoxide, and the first step is to convert from grams to moles. I'll try to write the steps here. Step 1, grams to moles, okay? And the reason is we need moles to relate these two things. They are not related by grams. So we add up a carbon and oxygen. So 15.999 is oxygen and 12.011 is carbon, and we get 28.01. Well, 28.010 grams per mole of CO. So our grams will cancel out, and we will now have moles. Okay, the next step is the mole ratio, just like we did up here. So step 2, you use the mole ratio to convert from what you started with to what you're solving for. Okay, and it could be two reactants, it could be reactants and products, it doesn't really matter. In this case, it happens to be a 1-to-1 ratio, which is totally going to not affect our numbers in any way, shape, or form. I'm just trying to show my work here. So for every 1 mole of carbon monoxide, we should get 1 mole of, this is methane, CH4. Now the last step, since we're solving for grams, is we convert from moles to grams of the product. So honestly, converting from grams to moles and moles to grams is not new stuff. We did that previous chapter. Converting from grams to moles, then using the mole ratio and then converting back is the new part. So we need to add up carbon and 4 hydrogens. So 12.011 plus 4 times 1.008. And I got 16.043. Okay, so we started out with grams of CO, that cancels out. Convert it to moles, that cancels out. Do the mole ratio to get from moles of reactants to products, that cancels out with this, and we end up with grams. In terms of typing this in your calculator, what I'm going to recommend is it's still just like unit conversions. You're going to take 20 divided by 28.010, hit equals. You take it times 1 divided by 1, but that doesn't actually affect anything, and then times 16.043. And the answer is 11.5, I guess. Okay, but the idea is it's always going to be these 3 steps in the same order. Okay. All right. I am going to talk about a really stupid analogy, and then we're going to do another example. We need to talk about something called limiting reactants, or the limiting reactant. Okay, so I apologize to any vegans or vegetarians in the room. I don't actually care if you're vegetarian, honestly. We need to talk about ham sandwiches. So let's say we have 9 pieces of ham, 11 pieces of cheese, and 26 pieces of bread. Okay, and our definition of a sandwich is 2 pieces of bread, 1 piece of ham, and 1 piece of cheese. Really boring, simple sandwich. Okay. And what we're trying to do is figure out what is the maximum number of complete sandwiches we could make. So based off this, we should be able to make 9 sandwiches. Based off this, we should be able to make 11. And based off this, since it takes 2 per thing, it's going to take 13. But what this means is we can only make 9 sandwiches. That is the maximum number of sandwiches we could make. We have enough cheese and bread to make more than that, but we ran out of one of the ingredients. It's the one that is limiting the amount of product we can make. Okay, so stupid analogy. Let's see it in a real problem. Okay, so essentially the thing that we just learned how to do, we're going to deal with what happens if one of these things runs out first. So let's try an example. So let's say we have this reaction. Magnesium and nitrogen form Mg3N2. And we want to know if we had 35.00 grams of this and 15.00 grams of this, how many grams of this could we make? So, just like the previous problem, one of these 2 things is going to run out first, but we don't know until we do the work. So, the first step is to balance this. This one's not balanced, so you have to balance it first. It's pretty easy. The nitrogens are balanced. We have 1 magnesium and 3 magnesium, so just going to put a 3 here. Pretty straightforward. Okay. I wish there was a shortcut to this, but essentially this 3-step process, you have to do it for both of the starting reagents and see which one runs out first. I wish there was a shortcut. There is not. So, what we do is we have 35.00 grams of magnesium, and we need to convert from grams to moles. So we look up magnesium on the periodic table, and its value is 24.305 grams per mole of magnesium. Okay? And the mole ratio is the second step. For every 3 moles of magnesium, we should get 1 mole of magnesium nitride. So the 3 moles of magnesium goes on the bottom because that's what we need to cancel out, and it has a 3 in the front. And we should get 1 mole of this stuff on the top. 3 and 2. Okay? The final step is to convert from moles to grams of this product. Okay? So if we add up 3 magnesiums and 2 nitrogens, I'm cheating from a problem that I already have worked up, comes out to 100.929 grams per mole of Mg3N2. You'll see that it's the same 3 steps, everything cancels out. In terms of typing this in your calculator, the way this works is you're going to take 35.00 divided by 24.305. I'm going to recommend you hit equals, then divided by 3, hit equals, and then times 100.929. Hit equals, and you get 48.45. Now here's the thing. This may or may not be the right answer. So kind of like up here when we did like, oh, we have 11 pieces of cheese, that can make 11 sandwiches. Based off only the cheese, sure, we could make 11 sandwiches, but we don't know yet if the nitrogen is going to run out, so we need to check. Okay, so we do the entire process again for nitrogen. So we have 15.00 grams of nitrogen. You add up 2 nitrogens, because it's N2, and that comes out to 28.014 grams per mole. And this time it's a 1-to-1 ratio, so for every 1 mole of N2, we should get 1 mole of Mg3N2. And it's the same product, so I can just recycle this last parenthesis. Okay, and we're going to type it in just like we did last time. So we're going to take 15.00 divided by 28.014. Okay, hit equals, and then times 1 divided by 1 isn't going to change anything, so times 100.929. And I got 54.04. So one of these is the right answer, and it's exactly the same logic up here. You do all this, whichever one's the smallest answer, that's the right answer. This is the one, the magnesium is the thing that ran out first. Mg is the limiting reactant. It's the one that is limiting how much product we can make. If we had more magnesium, we could make more product. Okay? Okay, now we need to introduce one more concept and then we'll be done with this video. We need to introduce the idea of percent yield. This is essentially a measure of how much you made compared to what could have been made as a percentage. So in the real world, so basically for this particular problem, if we had 35 grams of magnesium and 15 grams of nitrogen, and if literally every atom behaved exactly how we were expecting it to, and none of them like didn't react or form some other side product, we should be able to get 48.45 grams maximum. That is the theoretical yield. In the real world, the odds of you getting anywhere near that amount is pretty slim to none. Most reactions aren't 100% efficient. Percent yield is pretty easy to calculate. What you do is you take the actual yield, so if you were in the lab, how much you actually measured, divided by what was possible, which is the theoretical yield, times 100%. Okay, so the actual yield is what you measured. The theoretical yield is difficult to measure, or difficult to calculate, but it's literally this number. We already know how to calculate it because we just learned that. So for this particular example, let's try one. So let's say we had 35 grams of magnesium and 15 grams of nitrogen. We ran this reaction. If you actually got I don't know, let's say 37.51 grams of Mg3 and 2, what is your percent yield? Or what is the percent yield? Well, really all you're going to do is, I'm just going to plug the numbers in up here. You're going to take 37.51 because that's what you did get, divided by what you could have gotten, times 100%. Okay, and I just made these numbers up, so I don't know what the answer is. So 37.51 divided by 48.45 times 100. 4 sig figs on both of those, so 77.42% of what was possible. Okay. Percent yields. Typically with percent yields, a 0% yield means that your reaction did not work at all. Okay. And in an ideal world, I would love to tell you that 100% yield is the maximum. But in all honesty, if your product is pure, 100% yield is the highest value. But in the real world, if you have impurities in there, your value can actually be over 100%. And it just means that your product has other contaminants in there. Okay, so for most of the time, 100% yield is the maximum. But I will tell you, in the real world, I've had people report like a 450% yield in the lab before because they had all sorts of contaminants in there and their product sucked. So this is how you calculate it. Just be aware that it is possible to get over 100. It's just not likely. All right, thanks.